Black holes are supposed to be forever. That is the intuition, the cultural understanding, the image that has lodged itself in the popular conception of what a black hole is: an eternal darkness, an irreversible endpoint, the universe's final answer to anything that falls in. A one-way door that, once closed, stays closed. Forever. Stephen Hawking destroyed that idea in 1974. Not with an observation, not with experimental data, with mathematics, with a calculation performed at the border between quantum mechanics and general relativity. Two theories that describe reality in different languages and still have not been fully joined into one. At that border, where the physics of the very small meets the physics of the very massive, Hawking found something that should not have been there. Light, coming from a black hole, not from an accretion disk, not from gas heating up before it falls in, not from jets launched by magnetic fields outside the horizon. From the black hole itself, as seen from far away. A faint thermal glow associated with the event horizon, so dim that no instrument we have ever built could detect it from any ordinary black hole in the universe today. A black hole is not perfectly black. It leaks. Slowly. Almost impossibly slowly. Over timescales so vast that the current age of the universe looks less like a beginning than a rounding error. But it leaks. And if it loses energy, it loses mass. And if it loses mass for long enough, then one day the thing we thought was eternal reaches its final moment, until nothing remains. To understand how a black hole can die, you first have to understand something strange about empty space. Empty space is not empty. In quantum field theory, the vacuum is not a featureless nothing. It is the lowest energy state of fields that fill all of space, and those fields fluctuate. They cannot be perfectly still. Even in the coldest, darkest region between galaxies, the vacuum has structure. The popular picture of Hawking radiation is often told using virtual particles. A pair appears near the event horizon. One particle falls in, the other escapes. The black hole loses a little mass. That picture is useful. It is also not the full mathematics. The real calculation is stranger. What one observer calls empty space, another observer near a horizon does not necessarily call empty. The event horizon changes how quantum fields are divided into particles and no particles. The black hole's curved space-time distorts the vacuum itself, and to a distant observer the result is a stream of real thermal radiation moving outward. The energy of that radiation has to come from somewhere. It comes from the black hole. A little less mass, a little less curvature, a horizon that is almost the same size as before. Almost. This is Hawking radiation, named after Stephen Hawking, who derived it in 1974 by applying quantum field theory to curved spacetime and, in doing so, permanently changed what a black hole was allowed to be. Before Hawking, a black hole was a final state. After Hawking, it was a clock. The rate of that clock depends on mass. Smaller black holes radiate faster. Larger black holes radiate more slowly. The temperature of the radiation is inversely proportional to the black hole's mass. The smaller the black hole becomes, the hotter it gets. This is the opposite of ordinary objects. A coal cools as it loses heat. A black hole heats up as it loses mass. A black hole with the mass of our Sun would have a Hawking temperature of approximately 60 nanokelvins, 60 billionths of a degree above absolute zero. The cosmic microwave background, the leftover glow of the Big Bang that fills all of space, is about 2.7 kelvins. That background radiation is roughly 45 million times hotter than the Hawking temperature of a solar mass black hole. So a solar mass black hole today is not truly shrinking. It is absorbing more energy from the universe around it than it is losing through Hawking radiation. It is, by the smallest imaginable amount, gaining mass. For it to become a net emitter, the universe around it must cool below its own Hawking temperature. Only then does the balance change. Only then does the black hole begin the long final drain in earnest. And even then, the timescale is almost beyond meaning. A solar mass black hole, isolated in a cold enough future universe, would take roughly 10 to the 67th power years to evaporate. 10 to the 67th. The current universe is about 1.4 times 10 to the 10th years old. 14 billion years. A number that already defeats human intuition. A solar mass black hole's lifetime makes that number vanish. The black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million suns. Its evaporation time is around 10 to the 87th years. The largest black holes, with masses of tens of billions of suns, survive even longer, around 10 to the 99th years, depending on their mass. These are not timescales in the ordinary sense. They are not waiting periods. They are not futures you can imagine. They are numbers written at the far edge of arithmetic, where the universe has already burned its stars, exhausted its galaxies, cooled its background radiation, and entered an age so empty that black holes are among the only large structures left. And still, they are not forever, because the evaporation accelerates. As a black hole loses mass, it becomes smaller. As it becomes smaller, its Hawking temperature rises. As its temperature rises, it radiates more power. As it radiates more power, it loses mass faster. The process feeds itself. For almost the entire lifetime of a black hole, nothing seems to happen. The change is too small. The temperature is too low. The radiation is too faint. A solar mass black hole could sit through ages of cosmic history and appear unchanged. But near the end, the equations begin to run. The black hole shrinks. The temperature climbs. The radiation hardens. The quiet leak becomes a flare. In the final stages, if Hawking's semi-classical calculation continues to hold down to extremely small scales, the black hole would stop being cold. It would stop being dark. It would become a tiny, violently hot object radiating particles at an accelerating rate. The final seconds would not resemble a star exploding. They would not resemble a supernova. There would be no expanding shell of stellar debris, no shockwave through a giant atmosphere, no glowing nebula left behind. There would be a horizon smaller than an atom, then smaller than a proton, then approaching the scale where the known equations can no longer be trusted. There would be a burst of high-energy radiation, gamma rays, particles, a final release of energy from something that had once swallowed stars. For a fraction of a second, the death of a small black hole could outshine anything in its immediate surroundings. Not across a galaxy, not across the universe, but locally, unmistakably, a signal, the last light from an object that, by definition, was once supposed to emit none. And then the horizon is gone. Or at least, that is where the known calculation points. The exact final instant is not settled, because the black hole reaches the Planck scale, the scale at which quantum gravity must replace both ordinary quantum field theory and classical general relativity. Hawking's calculation tells us the black hole should evaporate. It tells us the evaporation accelerates. It tells us the temperature rises as the mass falls. But the last step is beyond the theories we currently possess. The equations lead us to the edge. Then the edge disappears. And here is what remains unsolved. When the black hole is gone, what happened to the information that fell into it? Everything that crossed the event horizon carried quantum information. Atoms, photons, magnetic fields, stars, planets, gas, light, the complete quantum state of whatever the black hole consumed during its lifetime. In ordinary quantum mechanics, information is not destroyed. It can be scrambled. It can become impossible in practice to reconstruct. But the underlying evolution is supposed to be reversible. The universe is not supposed to erase its own bookkeeping. Hawking radiation appeared to violate that. The radiation seemed thermal, random, featureless. It seemed to carry temperature, but not memory. If a black hole completely evaporated into radiation that contained no information about what had fallen in, then the information was gone. Destroyed. Not hidden. Destroyed. Quantum mechanics would fail. This is the black hole information paradox. And it is not a small technical issue. It is one of the deepest contradictions in modern physics, because both sides are supported by theories that work extraordinarily well. General relativity says the event horizon hides the interior. Quantum mechanics says information cannot simply vanish. Hawking's calculation says the radiation looks thermal. All three cannot be naively true at the same time. For decades, Hawking argued that information really was lost. Black holes, he thought, were exceptions to the usual rules of quantum mechanics. Many physicists found that unacceptable. If one black hole can destroy information, then unitarity, one of the foundations of quantum theory, is not fundamental. By the late 20th century, especially after developments in string theory and the holographic principle, the majority view began to shift. Maybe information is not destroyed. Maybe it escapes. Not in an obvious way. Not as a readable message. Not as a list of everything that fell in. But encoded in subtle correlations in the Hawking radiation, correlations so delicate that the radiation looks random if you examine it simply, but is not truly random in the complete quantum description. In recent years, calculations involving the Page curve, quantum extremal surfaces, replica wormholes, and islands have given physicists the strongest evidence yet that information can be recovered in certain models of evaporating black holes. This is major progress. It is not the end of the problem. These calculations are not yet a complete description of a real astrophysical black hole in our universe. They are windows into the answer. They show that the old picture, black holes simply destroy information, is probably wrong. Probably. But the mechanism by which information escapes, and what the interior of the black hole really means while it is evaporating, remain among the hardest questions in theoretical physics. The black hole dies. The mystery does not. There is another question hiding beneath it. What happens to the singularity? In classical general relativity, the singularity is where the theory breaks. A place where density becomes infinite, curvature becomes infinite, and the mathematics stops describing a physical world in any ordinary sense. Most physicists do not think the singularity is a real point of infinite density in nature. They think it is a warning, a sign that general relativity has been pushed beyond its domain. As the black hole evaporates, the event horizon shrinks. The classical picture says the singularity remains inside. But when the black hole approaches the Planck scale, the distinction between inside and outside, geometry and quantum state, horizon and no horizon may no longer behave the way our current language assumes. Does the singularity dissolve into quantum geometry? Does a Planck scale remnant remain? Does the black hole disappear completely into radiation? Does the interior connect to some region of space-time our current equations cannot describe? We do not know. The final moment of a black hole is not merely an explosion. It is a boundary in knowledge. It is the place where the two greatest theories of the 20th century both arrive, both speak, and then both stop being enough. Somewhere in the universe right now, this may already be happening. Not for a stellar mass black hole. Not for a supermassive black hole. Those are far too young, far too massive, far too cold. But primordial black holes, if they exist, could be different. They would not have formed from dying stars. They would have formed in the first fractions of a second after the Big Bang, from extreme density fluctuations in the early universe. Some could have been much smaller than stellar black holes. Small enough that their lifetimes are shorter than the age of the universe. If primordial black holes of the right original mass were created, some of them could be completing their evaporation now. Today, a final flash of gamma radiation from a black hole that was born before the first atom, before the first star, before the first galaxy. No confirmed evaporation flash has ever been detected, but astronomers have searched for them. Gamma-ray observatories have looked for the kind of short, hard burst that an evaporating primordial black hole might produce. Non-detections have already placed limits on how many such objects can exist nearby. That absence matters. It does not prove primordial black holes do not exist. It does not prove Hawking radiation is wrong. But it means the universe has not yet given us the one signal that would change everything. The detection of an evaporating primordial black hole would be the first direct observational confirmation of Hawking radiation. The first time the faint theoretical glow became an event in a detector. The first time a calculation from 1974 became a flash of gamma rays in the sky. It would be one of the greatest confirmations in the history of physics. And it has not happened yet. Hawking was 32 when he derived the radiation that bears his name. He had been diagnosed with motor neuron disease years earlier. His body was already failing. The disease had taken away much of what a physicist usually uses to work: the ease of movement, the ease of speech, the ordinary physical rhythm of writing and talking through equations. But the calculation survived. It survived in his mind first, then in the mathematics, then in the structure of modern physics. When Hawking told other physicists what he had found, the reaction was skepticism. It had to be. The results sounded impossible. Black holes were the objects from which nothing escaped. Now Hawking was saying they emitted radiation. Not because they were badly defined. Not because matter outside them was glowing. Because the combination of quantum fields and curved spacetime required it. He was right. The calculation has been reproduced by many different methods. Black hole thermodynamics, quantum field theory in curved spacetime, string theory, holography, analog systems. Different routes keep pointing back to the same terrifying conclusion. Black holes are not forever. A black hole formed when the universe was young can evaporate. A black hole that swallowed stars can shrink. A black hole that bent space-time for longer than galaxies shine can reach a final moment. And when it does, the universe is left with a question where the darkness used to be. Not only what happened to the mass, not only what happened to the horizon, but what happened to everything it knew. Every atom that crossed the boundary, every photon that fell in, every quantum state that entered the region from which, classically, no message returns. The black hole may die, but the information cannot simply be allowed to disappear. Somehow, if quantum mechanics is right, the universe remembers. Somehow, the darkness keeps a record. And the answer to how that record survives, the answer to what a black hole does with everything it swallows, may be the most important unsolved problem in theoretical physics. The black hole is gone. The question remains,